Hello. This is my presentation for molecular modeling. It's about explosive energy and how it is modeled in AMPAC. The purpose is to compare the difference between the published information on explosive energy released during a detonation and the results that AMPAC can provide. Some quick background information that is important for the rest of these results. Explosives usually break down into three main components. Depending on what is in them, obviously they break down differently. But for the most part, you're usually going to get diatomic nitrogen first, water second, and CO2 third. And it'll usually follow this hierarchy. So if you have a limit of hydrogens, they'll go to form water first before they form carbon dioxide, or in some cases carbon monoxide. One exception you'll see later is that TNT forms a lot of just carbon when it detonates, and it is a little bit frustrating for AMPAC to calculate. So here is triacetone triperoxide, commonly known as TATP. As you can see in the picture to the right, or in the formula on the top, that there's a lot of hydrogen, a lot of carbon, and a lot of oxygen. There's no nitrogen, so we start off right off the bat with an exception. This makes it difficult to detect in the past because most explosive detectors detect nitrogen. The TATP was not commonly used in anything until the last couple decades, until the internet and other sources allowed more people to find out how to safely make it. Until then, TATP was considered far more dangerous for the person making it than anybody they would attack with it. So there's the reaction on the top there. As you can see, it produces a lot of water and gas, not a lot of leftovers after an explosion. Its heat of formation is 21.59 kilojoules per mole. And after it detonates, according to AMPAC, it produces 1,504.27 kilojoules per mole. Now, information is still developing and new on this compared to things like TNT, which has been around since the Civil War. But I got results from about 1100 to 1500, which I kind of consider to line up pretty close to the 1504 that I got from AMPAC. I was really surprised that I was able to get such an accurate measurement. I'm assuming it's accurate. If the actual number is closer to 1100, then it's not as accurate, but it seems pretty accurate to me, and I'll call that a win for AMPAC. TNT, as you can see, this one has nitrogens, and there's the formula on the top. Heat of formation is negative 54.39 kilojoules per mole. And as you can see, it decomposes to 3 nitrogens, 3 diatomic nitrogens, 5 waters, 7 carbon monoxides, and 7 carbons. Depending on how rich an environment is in oxygen, you can get different results on this, where you would get a lot more oxygens involved. There's also another detonation process where instead of making H2O, you just make diatomic H, and the carbons become all CO or CO2. This one was a little more easy to calculate, and I think it's considered the main route. Detonation releases 2,907.23 kilojoules per mole, and that's with the carbon factored in based on, I just plugged carbon in and ran it to optimize just so I could see the result, which I know AMPAC doesn't really do, so that caused me some problems on that. I didn't know the best way to calculate that. But if you ignore it, you get 758.96, which is not really far off the 616.4. It's at least on the same scale. So I would also consider that a fair victory. It is impressive that you can see how much of a difference there is between the TNT here and the TATP there, and how AMPAC was at least able to scale with that, if not being exactly the same answers as what is published. HMX is a interesting explosive, partly because of how it looks, partly because of the naming. There's a lot of debate about why it's called HMX. What I was originally told was it was British and it stood for Her Majesty's Explosive. I don't think that's true. I've also heard high melting explosive and several other nicknames associated with it. I think just the British thought it sounded good when they designed it. But as you can see, it's an 8-member ring, alternating carbons and nitrogens. So there's a lot of mass on here, creates a lot of energy, which is deceptive when you look at the detonation energy on here and what was published on here. And to me, that was staggeringly low. Also, what I found for the published for the kilojoules per mole is 147 published. 104.77 kilojoules per mole for the heat of formation. AMPAC gave me about 65 kilojoules per mole. And produced 344.37 kilojoules per mole, which is a unique result to say the least. And this is a published result I saw, and I am almost certain this is wrong. But it was on the Navy database that I got the other ones from. But I don't know how that could possibly be true. RDX is similar to TNT, in at least the fact that it's on a same type of ring, and it has the 3 nitro groups on it. It's 83.82 kilojoules per mole to create. You can see how it breaks down. And this one was massively off on the detonation of what AMPAC gave me and what was published. And from what I've seen when RDX blows up, it's a pretty big boom. So I'm pretty sure it's well over the 325.4 kilojoules per mole. And I'm not sure what is going on there. Lead azide is a lot of pop and a little bang. So these numbers kind of line up. So basically when you detonate it, you're not going to get a lot of energy. I've been told you can actually hold these in your hand and not hurt yourself. It is a high explosive. It moves very fast, but it's a lot of pop and not a lot of push or shattering effect or brisance. So it's a pretty cool effect, but not extremely dangerous. Mostly that is used to initiate other explosives. And as you can see also, there is just one lead and nitrogen. So there's not a lot else on there to be excited about. So you lack a lot of the explosive oomph that you get from other explosives. But what I liked here on detonation, 61.16 kilojoules per mole versus the published of 87.34, and I consider that fairly close, especially because I was not exactly able to produce the ion effects that happen in lead azide when it's created. Urea nitrate was a little bit tricky, but if you'll notice the numbers are dead on, or really close for the detonation and the published. It's a ion explosive, so if you look to the right on the AMPAC picture, you will see that there's a nitrate ion and the urea, and you combine those and you get the 3 nitrogens, the 5 waters, and 2 CO2s, and you get a spare oxygen spinning off from the air. Yeah. Assuming that's the way it works. It would obviously detonate a little bit different in an anaerobic anoxygen experiment. The detonation on this one from AMPAC compared to the published detonation seemed very close. Alright, here's an exception I made. 94% ammonium nitrate, 6% fuel oil, number 2, is difficult to calculate, especially because you have a fairly long carbon chain in there. And I don't know how reactive it is, and it would throw off my numbers immensely. So I substitute it for ammonium nitrate and nitromethane, which is a smaller molecule, and it's more standardized. It's made the same way every time. Like, if you buy ammonium nitrate from a factory, it'll be made slightly different depending on the factory that it comes from. And then you also, fuel oils are different in every part of the country, or in every part of the world, and even in different parts of the United States. California fuel oil is significantly different than Texas, and that is significantly different than New Jersey. So it's very difficult to find a standardized information for this one. But once again, you will see that the detonation and the published energy released is very similar. And I was surprised that these are so high. I know they're used for blasting effects and not really used for the pop that we talked about with lead azide. So I think that translates more into the kilojoules per mole. And as you've seen Oklahoma City and Texas City and other bombings that have used this kind of thing, you can see how effective that ammonium nitrate with really any type of fuel can be, or any type of oxidizer can be. So generally, with one exception, AMPAC seemed fairly accurate, and the numbers at least moved on the right scale, except for that one exception, which could have been my fault, but I don't know how I could have fixed it. Anyway, thank you for listening, and thank you.